We're going to finish up our lectures talking about temperatures and temperature conversion. And this diagram will help you understand how we go about converting temperatures. This first shows the Fahrenheit scale, which is what we use in the United States. The freezing point of water is 32 degrees. The boiling point of water is 212 degrees. There are 180 degrees Fahrenheit between the freezing point and the boiling point. The same 2 points, the freezing point on the Celsius scale is 0, and 100 is the boiling point on the Celsius scale. So there are only 100 degrees of temperature in that same distance of heat. Kelvin is the same distance, but has a different baseline, 273 being 0 degrees and 373 being the freezing point. So if we're going to do conversions, the first conversion is easy. If you want to go from here to here, it's obvious all you have to do is add 273 degrees. So the conversion of Celsius to Kelvin is adding 273 degrees. Converting from Kelvin to Celsius is subtracting 273 degrees. Where it becomes a little more difficult, where you have to memorize a little formula, is to go from either Celsius to Fahrenheit or Fahrenheit to Celsius. So first let's look at going from Celsius to Fahrenheit. So you have a Celsius and you want to know what it is in Fahrenheit. First of all, you have to convert from 100 scale to 180 scale. Well, 180 divided by 100 is the same as 9 over 5. So it's 9/5 whatever the Celsius is. Then you also have to convert from a 0 to a 32, so you have to add 32. To go the other way, you just go the other direction, but you first convert 32 scale to 0 scale by subtracting 32. Then you multiply by 100 divided by 180, or 5 over 9. So let's look at a few examples and make some conversions for this. So let's start out looking at this first one, which is 22.4 degrees Celsius, and you want to find out what that is in Fahrenheit. Well, remember that to go from a 100 degree scale to 180 degree scale, you have to multiply by 9 over 5. Then you have to change it to the 32 scale by adding 32. I'll set all three of these up and then we'll go back and figure out what the answers are. The second one is 22.4 degrees Celsius to Kelvin. All you have to do is take 22.4 and add 273.15, and that gives you that answer. Then Fahrenheit to Kelvin. Now there's no direct conversion from Fahrenheit to Kelvin, so you have to first you take the Fahrenheit and convert that to Celsius, and you're going to go from 180 scale to 100 scale, so that's going to be, but first remember you have to change this to the 0 by subtracting 32, then multiplying it by 100 over 180, or 5/9, and that'll give you the Celsius answer. Then once you have the Celsius answer, you just add 273.15. So let's go back up here just for grins and figure out what this answer is. 20 is 4, 5 into 20 is 4. That leaves you 24, and 5 into 24 is another 4 and 8. So this is point, and then you multiply that by 9, and that's 72, and this is 36 times plus 7 is 43, and so this is going to be about 40.32, and then you add 32 to that, so it's going to be 72.32, but this is only 3 significant digits, so you drop this one, and it's 72.3. This one's pretty easy. It's 295.55, and again, You have 3 significant digits here, so you round this up to 296 Kelvin. This is degrees Fahrenheit. You always have to have a label, by the way. If you subtract 32 here, you get 9.6, I believe, minus 9.6. And then you divide that by 9, and you're going to get approximately, say, 7. And then multiply that by 5, and you get about 8.5. And that's negative, by the way. These are all negative. And then so you subtract 273.15, and you subtract 8.5 from that, and you get 264. Again, it's 3 significant digits, so this is going to be 264 Kelvin. And with Kelvin, you never say degrees. You just say Kelvin. With the others, you say degrees Fahrenheit or degrees, whatever. So let's finish up here talking about density. And density is something called a calculated unit, or a calculated measurement, as opposed to a direct measurement. And it means that you can't directly measure a density. The density is found by multiplying two, or dividing, or doing some mathematical manipulation with two other measured entities. And in this case, in order to do this, first you have to know that volume is the amount of space that matter takes up, and there are geometric formulas that can be used to find volume, or you can use fluid displacement to find volume. When an object sinks in a fluid, it displaces its volume. Fluid displacement equals the volume of fluid plus the object minus the volume of the fluid alone. So whatever is displaced represents the volume of the object. Density is the mass of the object divided by the volume of the object. So D is equal to M divided by V. In this case, rho is a Greek letter that's commonly used to represent density. M is mass, and V is volume. So here's an interesting little example. What we have here is our graduated cylinder, which shows the volume of the fluid to be approximately 13.5 milliliters. When you put the rebar in there, the final volume is 22.4 milliliters. The displaced volume would be 22.4 minus 13.5. So 22.4 minus 13.5 is equal to 8.9 milliliters. So that's the volume of the rebar. The density of the rebar will be its mass, which is 69.658, divided by 8.9. Now the calculator tells you 7.8267415, but because 8.9 only has 2 significant digits, then the answer, 7.8, also only has 2 significant digits. Here's a piece of gold. The initial volume of the fluid by itself is 17.1 milliliters. The final volume is 19.8. And the mass of the gold is 51.842. The displaced volume is 19.8 minus 17.1, or 2.7 milliliters. So that's the volume of this piece of gold. The density would be 51.842 divided by 2.7. The calculator gives you this answer, 19.000741, but you round that to 19. Now you see here I put 19.2. There's an argument here, because is the tenth digits the best? But if you follow the rules for division, it should be 19 as the answer. So let's do some other problems here. Let's look at the first one. 452 gram piece of metal displaces 22.5 milliliters of water. That tells you that the displaced volume here tells you that the volume, rho, is going to be mass divided by volume. And so you're going to have 452 divided by 22.5. And the significant digits here are going to be 3. So 452 divided by 22.5 is equal to 20.0 and then a bunch of stuff. But it's 20.0888 repeating. You round this up to 20.1 grams per milliliter. The second here is a 1.67 kilogram, be careful there, piece of wood has dimensions of 1.1 cube, okay? So the volume of a cube is the side of the cube raised to the third power. So the volume here is going to be 1.1 times 1.1 times 1.1, or 1.331. Now, I don't do significant digits in an intermediate calculation. I only do it at the end, okay? So I don't round this up to or down to 1.3 because you compound your error if you do that. So this is cubic meters, and so you have a 1.67 kilograms. That's the mass divided by 1.331 meters cubed. And if you want this, you can say this is 1.67 divided by 1.331. So this is going to be, now this is two significant digits. So the answer here is 1.3 kilograms per meter cubed. But what if a person wanted this in centimeters? What would you do? What if they wanted, say, grams per cubic centimeter? Well, you would have to express this number as centimeters and this number as grams. But it's perfectly appropriate, as long as you write the units down, to write it down like this. The last one here, it says a 6.55 pounds of metal displaces 0.122 cubic feet of water. So that here the density, and we're not going to get into technicalities here. There's actually a mass density and a weight density, and this is actually a weight, but I'm not going to do that in this example. But so this would be 6.55 pounds divided by 0.122 cubic feet, and that's going to be 6.55 divided by 0.122 is going to be 53, and the significant digits is 3, so it's 53.7 pounds per cubic foot. Now, in the future, we're going to be talking about the difference between a mass density and a weight density. These two are mass densities, and this one's a weight density. But for this sake, if I give you a problem like this, just don't worry about that. Just do pounds per cubic foot, just as long as you get this unit here and you put that down. So that ends our lecture today. Make sure you bring your questions to class, because we covered a lot of material today, and we'll go over problems until you understand temperature conversion or significant figures or density calculations, etc.